B2 acceleration. This is another quantity that arises naturally in kinematics, and this deals with the change in the motion. Now, back in 2009, I published a paper on kinematic measurements from YouTube videos in the physics teacher. That was the first publication using YouTube in some way to teach physics. And then since then, of course, there's been a lot of publications and examples. The example that I did, one of them that helped me get inspired, was one that involved a BMW motorcycle, like this one here. And in the YouTube video, it accelerated and showed the speedometer. Now, the particular video I used, some believe that the author used a little bit of trickery and the data may not be 100% authentic. However, if you take this data as given, this is reasonable data. This could be very, fine, because it's within the range of speeds for the bike. And we will go ahead and take this as a given, which I did get from the video by watching each second, like stop the video and write down in kilometers per hour. To get an idea of the concept of acceleration, let's make a little chart where we have the time in seconds and the speed in meters per second, and say a time t equals 0, the speed is 0. So this could be represented by t and the speed by the letter v. Then after 1 second, say we're going 2 meters per second. And then after 2 seconds, we're going 4 meters per second. And after 3 seconds, 6 meters per second, and so on. 4 seconds, 8 meters per second, 5 seconds, 10 meters per second. So here, the change in velocity at each step, if we look at this, it's gaining 2. It's a plus 2, a plus 2, plus 2, plus 2. And we call that delta V. This is the Greek letter delta, uppercase delta. Lowercase delta is this one. Delta V is the change in velocity, and you can think of it as a final velocity, minus an initial, or the second velocity minus the first one. So this is the initial, this is the final, and then this becomes the initial, and then that's the final for the next consideration. So in that case, we're seeing that the acceleration, the concept of acceleration, is we're gaining 2 meters per second. Now, whenever we do per, we do a denominator for the location. So this is 2 meters per second, and don't mind the 2 seconds there. We're going to write that as 2 meters per second squared, and that's the unit for acceleration. So this 2 meters per second, you can think of that as a delta V, is your 2 meters per second, and since the acceleration is constant, every second it's going to be the same. And the delta T is the 1 second, and by taking delta V divided by delta T, that's our concept of acceleration. So we can write this out formally as the acceleration is the change in velocity over the change in time. And here we can, since it's constant, we can take the final one, the 10 meters per second, and subtract 0, the initial one, taking it that way, and then 5 seconds compared to 0 seconds, 5 seconds minus 0 seconds. And this is 10 meters per second per 5 seconds, which reduces to the same answer we got before, 2 meters per second squared. So this general formula here, which we can write out as a final minus initial velocity over a final time minus initial time, is our acceleration definition. Now, what we would like to do with this is related to concepts in calculus, where you take the delta t to be smaller and smaller and smaller to get an instantaneous acceleration. So when we do that, we write the limit as delta t goes to 0 of delta v delta t. Now in that limit, the delta t will become 0 and the delta v will, but the ratio will not be. And that's very important. We don't divide by 0. We're looking at the instantaneous acceleration. And we can play the same arrangement with the velocity, which is considering the change in the position over the change in time, where here the time delta goes to 0. So this is our velocity, the change in distance per time. So if you went 2 kilometers in 2 hours, you'd be going 1 kilometer every hour. So these concepts are very, very important in kinematics. Now, I'd like to leave this section with a very, very important formula, the form of it, and that is to take this formula and consider the final one to be simply v, and the initial one here to be v sub naught, or v sub 0. This is a standard notation. It's very, very powerful. And then the final time to be t, and the initial time to be 0. In other words, we start the watch when the problem begins. So when we do that, the acceleration here is v minus v naught over t minus 0, which is v minus v naught over t. And then we can write that as a times t is v minus v naught, and then adding the v naught to each side of the equation, and we'll write the v on the left is v naught plus at. A very, very important basic equation in kinematics.